We are celebrating the third workshop of the Hydrogen Technology Observatory, focusing on technical developments on electrolysis system. First of all, let me extend a warm thank you to all the online and presential attendees for joining us today. And now I have the pleasure of introducing our CEO of Enagás, the promoter of this observatory, that will officially welcome you. Thank you very much.
Thank you, Igor. Good morning, everyone. These are going to be just a few welcome words. Welcome to this, as Igor said, new workshop of the Hydrogen Technology Observatory. Today, we will put our focus in a key element of the hydrogen value chain, which is the electrolysis system. This is something key to really strengthen, accelerate the development of the hydrogen ecosystem. Today, we will have very relevant participants. This is a workshop co-organized with two of the partners of the observatory, the Aragon Hydrogen Foundation, which will open this session today, and Repsol. Today, we will be knowing one of the pioneering initiatives in Spain, in the Petronor industrial complex in the north of Spain, where Repsol is beginning to operate the first electrolyser built in our country, already in operation in an industrial site. We will have also two very relevant electrolysers manufacturers, Cummins and Nordex. And I think the good news are that although the technical challenges are very relevant, the progress is going very fast, and the maturity of the technology sector for electrolysers is being already very important to allow for the deployment of hydrogen, green hydrogen manufacturing at scale. I think this is one of the key elements that we intend to address today. We also want to show how this forum, this observatory, this kind of events is key to the creation of the ecosystem, which will strengthen and accelerate, as I said, the deployment, the advancement of green hydrogen. This is the aim of the Hydrogen Technology Observatory. This month of April, we are celebrating the first anniversary of the observatory with already 53 leading partners in this initiative, showing the value of alliances, of collaboration to really make sure that the hydrogen economy and the hydrogen ecosystem is happening when it is needed, also to comply with the very ambitious targets of decarbonization in Europe. During this year, the key lines of interest of the Technological Intelligence Working Group have been established. We have carried out 2 events, 2 technical workshops. We have disseminated papers, studies. We think this initiative is really gaining traction and is really taking off. We have already a community in our LinkedIn profile with more than 1,200 partners, members already. The observatory will also play a very relevant role in the upcoming second Enagás Technical Hydrogen Day. It will be celebrated on June the 11th, and we will have there a very strong role by the members of the observatory with the participation of very prominent national and international stakeholders. So let's work together to continue showing how cooperation is going to be key for the hydrogen economy. And please, we have Vanesa from the Aragon Hydrogen Foundation to open this session. Thank you.
Thank you, Arturo. Now I am delighted to introduce Vanessa Gil, a key contributor to today's workshop. Dr. Vanessa Gil, PhD in Science, is ARAID Senior Researcher and Head of the Research and Development at the Aragon Hydrogen Foundation. Recently recognized with the RENMAT Women in Renewable Hydrogen 2025 Award, Vanessa brings over 20 years of experience in hydrogen technologies, specializing in both high and low temperature water electrolysis. The Hydrogen Foundation of Aragon is a vital partner of the observatory because of its expertise and its relevant trajectory. And therefore, Vanessa will moderate the following roundtable. Please, Vanessa, the stage is yours. Thank you very much.
So thank you, Igor, for the kind introduction, and also thank you, Enagás, for the invitation to the Aragon Hydrogen Foundation to this workshop today. So as we heard just in the opening, we will facilitate today a knowledge technology exchange, and also we will drive forward the key innovations into the electrolyzer systems. We will hear from two speakers, one from Accelera by Cummins and also from Nordex, about two mature technologies, alkaline technology and also PEM technology. But also there are more technologies in the sector. So first, I would like to say why electrolyzers. As we heard today, and we have heard during a few years, electrolyzers is a key technology for low emission hydrogen production. Why this? Is because electrolyzer enables to produce hydrogen that is needed for future energy market and sector. But also electrolyzers also enables linking sectors that they were not linking until today. So, but before we start with what we'll discuss today about the challenges and also how is the status of the technology today and the prospects and where we go in this path, let me first give a few words about how is the status today about about the electrolysis capacity. The electrolysis capacity for dedicated hydrogen production has been growing in the past few years, but the market is true that is moving slowly than it was expected. As you know, last year, Europe should have had 6 gigawatts of electrolyzers installed, and also the production should be 1 million tons of hydrogen. This is too much. We haven't reached this milestone so far, and according also to the Clean Hydrogen Monitor from the European Hydrogen Association, today we have almost 400 watts of installed capacity, and also approx 60-something thousand tons of hydrogen has been produced. This is not enough. Also in Spain. In Spain, we have right now a few megawatts of electrolyzers, and we might reach a few gigawatts, and this is too much and a lot. This is, I would say, an opportunity to our country, to Spain, to attract investment, also to attract electrolyzer manufacturers to our country, also linked to our renewable sources that we have. And also in this path about how we see our country and what could be, we should think about electrolyzers from the technology point of view. The electrolyzers are being manufactured today. It is a reality. We can buy this kind of systems, but still there are some challenges. and still we could improve these systems. We could improve the systems in regards of the lifetime of the equipment of the system, also regarding reducing, of course, the cost, always important. If we can save some money, it's always good, but also improving the efficiency. This is also very, very important. Apart of this, there are other key innovations that maybe we will hear today, and could be related to different modes of operation. Could be high pressure, for example, or could be other changes in the standard operation conditions of these systems. Yeah, I said in the beginning, we will talk about alkaline and about PEM technologies, but there are more technologies. The reason because we decided to go to these two is because they are the most mature technologies in the market right now. There are also other technologies that they were some years ago very in this in this scale quite low, and this TRL scale they were very just in the beginning of this scale. And this is, for example, solid oxide electrolysis. But it's true that, for example, this technology is quickly scaling up its maturity. For example, in April 2023, just to give you a few numbers, 2.6 megawatts of solid oxide electrolyzer was installed in Netherlands in a refinery from Neste. And it was, or it became the biggest at that time. But only a few weeks after, the record was broken with 4 something megawatts solid oxide electrolyzer system in California, in NASA. Bloom Energy also, we discussed a few minutes ago, Bloom Energy has increased his capacity. And also here in Europe, we have Topso, for example. Topso, its core of business is about high temperature electrolyzer systems. And they are right now finishing or finalizing I would say would be one of the biggest manufacturing capacity installations in Europe, with 500 megawatts and expectations to be up to a few gigawatts of capacity. Also, we have anion exchange membrane. Anion exchange membrane technology is even less mature, we would say, but still we can buy these kind of systems today. So even though they are smaller in size, but they are there. Anion exchange membrane, we will not go into detail, or I'm not going into detail, but it's kind of hybrid. I always say it's a hybrid between alkaline and PEM. And then, just to summarize, there are some challenges, as I said, that we should look into these kind of systems. We need to reduce the cost, of course, and also there are some remaining challenges, as for example, system efficiency, and for some specific technology, also the use of critical raw materials, for example, or materials that are precious. This is also something to take into consideration. I wanted also to highlight that tracking the evolution of electrolyzer efficiencies is a bit complicated. Why? Is because, of course, we want to compare different technologies. Each technology is different from the other, and also the application. Depending on the application, on the conditions, the efficiency could be seen in a different way. In any case, more or less, alkaline and PEM, they are quite close in efficiency. If we look into high temperature, for example, solid oxide electrolyzers, the efficiency is different, but because of the core of the technology, because there we have like high temperatures, and then if we take into account different parameters or boundaries, then of course the efficiency increase. But this is one of the examples because we cannot compare exactly the number in efficiency, but we should look more into detail in the technology and the application. Just to finalize, because we want to discuss a lot today, and we only have a few minutes or half an hour, let's say. I would like to highlight also what we are doing in Aragón Foundation. In the Aragón Foundation, we have a long track record in the testing of alkaline water electrolysis. So it's something that is also in our DNA, as I said. We have been for a lot of years testing stacks. Always in alkaline water electrolysis. And the reason it was because at the time when the Hydrogen Foundation was founded more than 20 years ago, it was the most mature technology at that time. And because of the reason, because Hydrogen Foundation was created, it was the technology that it was selected. In this way, we have had during all these years, have the chance to build up 2 testing facilities. We have one that we call it industrial scale. We are possible to to evaluate stacks under state-of-the-art pressure and temperature at industrial scale, just a few cells, of course, but at the size of the industrial scale. And also we have a pilot scale test bench enabling operation of up to 60 bars. This is very high, but as we will hear maybe today, if not, I will let you know later. But also there are some innovations about going to high pressure electrolyzers. And our testing facility is able to test 60 bars and up to 120 degrees. This is kind of unique test bench in the environment to test this kind of task. And just to finalize, before I start with trying to introduce our speakers, in this regard, the projects where we are involved so far are 2 ongoing projects. And also we have private projects, of course, because we have this kind of unique testing facilities. So we have also collaborators that are interested in this to explore the technologies or to explore the evaluation of their key innovations. So right now, I'm coordinating one European project. This is called a HYPREL. HYPREL is about trying to advance in the alkaline water electrolysis from the point of view of try to develop high pressure systems or stacks, sorry. So the idea is try to see where is the limit for this, the output having produced about the pressure. There, we are leading the testing of the stacks at pilot scale. And also we are involved in other projects. This is called Endure. Endure is also about alkaline water electrolysis. And there is different. There is trying to prove the stack with the state-of-the-art conditions, but try to test and with innovative equipment at the stack level. So by the first time, we will evaluate from very kind of specific, let's say, equipment. It's called ACE. This is about trying to do impedance spectroscopy, very technical, but you should know that this is kind of special and very innovative equipment that also we can do not only at cell level, that it was until today in the lab, but also at scale level. And from them, we can get very useful information and the relevant environment, how is the behavior of each cell inside the stack, and maybe even try to provide feedback to the stack designers or to the stack manufacturers about how to improve even more the stack. So now we will start with our speakers. So I will introduce first Anne Murray. So Anne Murray is coming from Accelera by Cummins. She works in the electrolyser division, and she's customer solutions engineering director. So let me check here. Yes, Ms. Murray has over 25 years of managing complex engineering projects. She started her journey in hydrogen in 2012 by joining Hydrogenics, now Accelera. If I am right. She was responsible for managing several programs in both mobility fuel cells and stationary hydrogen generation applications. In this role, she oversaw multiple world first breakthrough projects, I would say. This includes, for example, the design and delivery of custom fuels and custom fuel cells engines for the world first commuter trains in Germany, and a large-scale power-to-gas plant in Ontario, first of a kind in North America, and one of the largest in the world at that time. She then led the design and delivery of the HyLizer 1000 product, first installed in a water electrolysis plant in Quebec. And it came online in 2020 and was the world's, again, largest, in this case, PEM plant in operation at that time. And was subsequently responsible for developing next generation PEM water electrolyzer products. And in 2023, so quite recently, Anne decided to leave R&D. I'm not sure if you are happy or not, I'm sure yes. And so step back into her customer-facing project execution routes by taking one of these director roles. So please, Anne, you want to join me? And also I will introduce our next speaker. And then the idea is that they will give a few slides, introduction of Accelera and also Nordex, and then we will continue the discussion. So Javier is mechanical industrial engineer from Navarra University. His work experience began circa 30 years ago, and in the engine block foundry for the for the automotive sector, where he performed engineering, quality, and manufacturing functions, becoming deputy to the head of one of the production sectors. So in 2000, he started his journey in renewable sector and in the turbine engineering department, becoming head of the industrialization and product support. And then in 2019, he became head of operations and maintenance of the division of Nordex, managing this department. And in 2022, he changed to the position which currently hold as a technical manager of for the development of an electrolyser within Nordex electrolyser technology. So please, Javier, we will just start with the slides. So please, Anne, I think that, yes, you can, yes, if you want, I can take this one. So please, Anne, if you want just to start the slides, yes.
Okay, oops. Yeah, so very quickly, I'm going to run through a handful of slides to introduce Accelera by Cummins. Accelera is the zero emissions branch of Cummins, which has historically been known more for its diesel product, diesel engines and power gensets. So the Accelera division comprises the zero emissions mobility as well as the electrolysis part, which is the business unit that I'm a part of. You can see here that Accelera and Cummins are well represented globally. We have a footprint all across the world, and we have been doing industrial development and technology deliverables for over 100 years as a business. So we're bringing that DNA of quality, consistency, and manufacturing scalability into the electrolyzer business. In terms of the electrolysis business, we have the world's largest PEM stack proven in industrial applications. We have been working with this PEM stack for about a decade now in this form factor. This is the current generation, has about 2.5 to 3 megawatts of installed capacity per stack. The Hylizer 1000 that was mentioned during the intro, that comprises of 2 stacks to deliver 1,000 normal meters cubed per hour in a single integrated unit. So that is, and we have also a smaller platform called the Hylizer 500, where we can deliver a turnkey solution for in applications where you're looking for 200 to 500 normal meters cubed per hour. In terms of some of the projects where we've been using this technology, it's been in, as I said, in in projects in industrial scale applications for almost a decade now. Some of them actually are projects I've had the pleasure to work on. Air Liquide Bécancour, that was the first project that used the 1000 that came online in 2020. I had the pleasure of leading that project team. It was a fantastic project. The India project that you could see beside it, that also I had the privilege of visiting that site last year. Mallorca is here in Spain. Some of my team members were there just a few weeks ago, in fact. Today, the NextEra project in Florida, we broke our own record, and we'll be breaking a record again in a few months, so stay tuned in terms of the largest PEM electrolysis plants. Today, the Florida Power and Light project is the largest in operation. But I said that'll be changing shortly. And then again, next year, we'll be breaking our record again when the 100 megawatt plant in Germany comes online. That's a project that is currently in manufacturing in our facility here in Spain, in Guadalajara. So if any of you have had the ability to visit that site, that's the project we're building today. So yeah, I think in terms of summarizing, I just want to say that while Accelera is a very new brand, it's only 2 years old as a brand, the DNA in electrolysis is very deep. Our business has been working in this industry for over 7 decades now, working with everything from atmospheric PEM to, atmospheric alkaline, pressurized alkaline, and today pressurized PEM. And I've had the pleasure of working with those technologies in my career. We've got a very large install base in applications, in industrial applications today in PEM. As was said, this is not in development. This is ready, available technology. And and also Accelera as a brand is still Cummins, and Cummins is of course known for innovation and reliability. So we want to make sure that that brand promise stays true in the electrolysis business as well. Thank you.
Thank you, Anne. Now, Javier, please.
Well, Nordex Electrolyzer is a spin-off from Nordex. Nordex is one of the bigger wind turbine manufacturer in the world. So the spin-off was created in 2022. It's 85% belongs to Nordex Group and 15% belongs to Sodena, that is the Navarra's government society for development. Really is the second largest investment in Navarra in a new industry. Our target is to, we started analyzing the hydrogen business 5 years ago in order to, let's say, look for the hydrogen as an energy vector for increasing our core business that was and that is the wind turbines, okay? So we decided to analyze the market, and we start seeing that there are many electrolyzer manufacturers, but with not enough strength for, let's say, for supporting big projects in remote location. Our target was really to go for remote location with a high potential in wind, mainly, like, I don't know, south of Chile or whatever, and combine or make an hybrid project between wind, solar, and electrolyzer. So at the end, we decided to go for our own development based on the strengths that we understand that the Nordex Group has developed during more than 35 years in the wind industry. And we decided to go for our own development. We choose the alkaline technology because on those big projects, we consider that there are some advantages for the alkaline technology, and there are some disadvantages, for example, with the PEM and so on, but that could in some way be reduced using a huge power plant, like the flexibility or other things, okay? Our product portfolio is going to be based on a 2.5 stack also as a base. And later from this base of a stack, develop different modules in the coming 2 years, we will be developing the 5 and the 10 megawatt modules, okay? But basically, we understand that this need to be, or to take advantage of scale economy in order to reduce cost. So we are going to develop, let's say, a base of product, but later combining those stacks, develop modules for bigger power plants. Okay. The roadmap, obviously, we don't have as much as experience as Cummins. We have been, we built a first electrolyzer with 50 kilowatt. A second prototype was built and commissioned last year with 500 kilowatt. We are proud of this prototype because we considered it like the biggest electrolyzer developed and manufactured and commissioned in Spain for that time. This year, we are going to commission in summer, probably the 2.5 megawatt electrolyzer. And next year, we will be developing the different modules for those with the objective of those big power plants. Okay. Regarding timeline on the upper line, you can see what I explained in the previous slide, but in the lower line, you can see our intention for the manufacturing capacities. So we are taking right now for the prototypes and for the pre-serials, we are taking advantage of the workshop that we have on the wind industry, on the wind turbines. So taking advantage of those experienced people, assembling, cabling, and so on, of the tools and so on, we are going to start like a kind of manual assembly. Reaching 100, we consider that in one workshop we can build 100 megawatt there in a couple of years. And in 2027, 2028, we will be building a kind of automatic plant in order to cover the needs of those projects in remote location that has been or that are being developed right now. Okay. Nothing else from Nordex. In 5 minutes.
Thank you very much, the both of you. And now we will start with the discussion. So we have here, as we said, one representative from the alkaline technology and the other one from the PEM. Both technologies are different, but of course, I assume and I believe also that there are some complementarities between the two of them. From your point of view, which are the main characteristics, technical, please, contributing to such synergies? So please, who wants to start? And then, yeah. So please, Anne.
Well, I guess I can start. Like I said, I've worked with both alkaline and PEM technologies. I do think the obvious advantage that alkaline has is, of course, in terms of, you know, the cost per stack is lower. Although I do question at the total installed cost level, we see that PEM does have a lot of advantages because of the scaling and the size and the highly integrated nature of the equipment. The other advantage from a PEM technology perspective is it has very low turndown. It has very high efficiency, and that's, of course, roadmap is going to continue to improve that. It also has a really good flexibility in terms of rapid response time to change in energy input levels. So today's applications are mostly PPA, direct coupled to grid. So, you know, the flexibility isn't as critical, but as we move forward in time and we're direct coupling to renewables, wind or solar, the flexibility is going to become a more important aspect of the overall project feasibilities. And then, you know, we do, because of the flexibility, there's a very wide range of operating from low turn down to higher current densities, which can help overall reduce the amount of stacks you actually have to install to match your energy profiles. So.
Yeah, it's true that, for example, the PEM technology has more flexibility. So if you want to connect one electrolyzer with one turbine, it's better, the PEM technology, because you are going to take advantage of most of the power curve from the turbine. But it's true also, and as Anne has mentioned, that, well, we decided to go for alkaline for two main reasons. One was the cost, as Anne has mentioned, and it was not only a question of cost, it was also a question of not having material that could put you in or that could limit your growth, let's say. Because at the end, the use of PGM materials, obviously iridium and so on, is more or less restricted to some quantity. And if the market is going to grow as it was expected, probably right now it's more stained. But well, if the market is going to grow, probably you could have some problems with the material. And it's not only a question of cost. And the other one is the durability. It's true that probably PEM is having more efficiency in some cases, but in those kind of big projects in remote locations, if you can work with the same stack for a couple of years more, makes a huge difference on the OPEX, let's say. So we decided for those two reasons. But it's true that right now, and the people that is developing those big projects are analyzing if a combination from, let's say, you put more power than electrolyser on those big projects. So it's true that probably the alkaline could make the base of the consumption and the production. But later, if you have PEM technology inside the same project, you can react quicker to the fluctuation, and you can go with less time, with flexibility and so on. So I think that could be complementary, but in big projects.
Yeah, so this was my question, right? In the beginning, even though there are some differences between the two technologies, but this is what it became like an added value, this complementarity for real projects that we have a real challenge to solve and to find a good solution. Always, the best solution always is a combination of different options. And as you said, alkaline and PEM would be quite good for this. Regarding, you said something about efficiency, durability, lifetime. I would like go into detail here. So the improvement of the electrolyzer efficiency from the point of view of the stack, but also the balance of plant is one of the key aspects, of course, because we want to improve the energy efficiency to reduce the cost at the end and so on. So from your point of view or your perspective, which is the level of efficiency that today Nordex and Accelera technologies possesses, and which could be the efficiency limit, if this is something that you can share, of course, in 5 years, for example, time, or what is the path where we go in terms of efficiency, but also I would like to discuss in terms of lifetime also, because both of them could be kind of related. So please, Javier, for example, this time.
Well, from our side, we have made some analysis of the LCOH at the end, and obviously the efficiency is a quite important factor, but it's depending on the project, let's say. So if you are achieving a kind of cheap electricity, the efficiency could be less important, let's say, in some way. And from another point of view, as I mentioned before, the lifetime probably could take some importance if you, let's say, if you can extend the lifetime of the stacks for a couple or 4 years more, let's say, on those kind of big projects. But regarding efficiency, it's true that as better efficiency that you can have, better cost of the OPEX and the electricity and so on. And in our case, well, we wanted to, let's say, in some way, from the 2.5 product that we are being developed, or that we have developed, we want to have some variant, let's say, in some case, increasing the efficiency or improving the efficiency, and in some case, increasing the lifetime, for example, just reducing the, for example, the diaphragm resistance. In our case, right now, I can give you numbers because we have been testing the efficiency for a long time in our prototypes. We are obtaining a 4.8 kilowatt hour per normal meter cubic. That's in the nominal power, but because we are going, let's say, to the limit of the current density that we consider that the alkaline could go, that is 600 milliamps square centimeter, and we are obtaining 4.8. Obviously, in lower points, or if you go for, I don't know, 50%, you can reach 4.5 because the efficiency is getting worse as much as the current density. Probably in both technology. I'm not an expert on PEM, but and for the future, with this kind of analysis, mainly on the stack, because it's the most, let's say, the big contributor to the efficiency, analyzing different electrodes in order to reduce the voltage, different diaphragm, and so on. We wanted to reach in 3-4 years' time 4.3 in nominal power. That's our idea for the future.
Thank you.
Yeah.
Listen.
Yeah, I think I can pick up on some of that. I think, yeah, they are definitely related. So in our product, our roadmap, we're actually looking at increasing the current density while improving or maintaining today's efficiencies. The other way of looking at it is we are giving you the same amount of hydrogen today at a better efficiency. It would depend on the application, how you would want to use that flexibility of PEM. In the technology, the amount of hydrogen is directly proportional to the amount of current you put through the stack. So when we talk about running at higher current densities, that means getting more hydrogen out of the same stack footprint. So that is our roadmap. We are looking to maintain our very compact, highly efficient product and to be able to drive it harder effectively and get more hydrogen out of it without compromising on durability or efficiency. So it's not so much about necessarily efficiency improvement so much as capacity increases without impacting efficiency. And it was a trade-off, right? You can always optimize for your specific application, which one's more important. But yes, as we move forward, our roadmap is to definitely, significantly increase the amount of capacity in our existing stack footprint. So that's the important piece. And then on durability and lifetime, that has to go hand in hand. So again, coming back to the reliability piece, it is important as we release next generation technologies that we have convinced ourselves that we have not impacted the lifetime in a negative way. The nice thing with our install base today is we're getting more and more data coming from the real world in real applications. We're able to collect and consolidate. You were talking about the importance of being able to measure the cells. We do that with every single stack on every project. So it's really starting to become a not yet a statistical significant amount, but an important amount of information that is helping to inform our roadmap and inform our lifetime projections and ultimately guarantees. So that all efficiency, capacity, and durability, they all have to be kept in lockstep with one another in the roadmap development.
Thank you. And we talk about efficiency and durability. So as you said, depending on the operation will be different. Maybe there's a specific case for a specific equipment, of course, and maybe a different technology or a solution to be provided. But and also stack or a system during the operation, we have different processes, right? Or different steps. We could have like a ramp up, ramp down, and also specific periods where the current density should be very high or very low. All these factors impact, of course, in the electrolyzer lifetime. So we have also even the pressure. It's not the same. I can assume that it's not the same if we operate it at high pressure, 30 bars, or a few bars. I don't know if this is a parameter, maybe depending also in the technology. But from your point of view, and considering alkaline and PEM technology, which is the operating condition from the following list contribution to the degradation of the electrolyzer? So we could say a few processes, maybe in the alkaline is maybe more critical, I don't know, ramp up and down or not, and maybe in the PEM is a different. So we have ramp up and ramp down, pressure fluctuations, for example, temperature fluctuations also. It's not the same. The temperature maybe fluctuate, current density, of course, and dynamic power profile. From your perspective, which is the more detrimental for the alkaline and for the PEM? And because of this, you also, of course, we need to look into the degradation mechanisms to try to improve the technology, of course. So could we develop on this list? Which is the most critical, for example, for alkaline? So please, Javier. Yeah.
Well, it's true. As I mentioned before, for us, the durability is one of the key aspects of the technology. Mm-hmm. And we have been performing a lot of tests on lower scale, let's say laboratory scale and so on. Even we have developed like a kind of internal let's say, accelerate lifetime test in order to check what's the, let's say, the bigger contributors to the durability. And in our case, in the alkaline, because probably it's more or less the same, but in our case, the biggest contributor is the switching off and startup, frequent switching off and startups, let's say. Because at the end, you are generating a kind of inverse current that is damaging a lot the electrode. Because the degradation is produced mainly on the electrodes. So the main contributor for the moment is on the alkaline is the switching on, starting up again. Later, more than the fluctuation, is the current density. If we increase the current density above the 600, we have been testing this, and at least in the alkaline, obviously with different electrodes, material, and so on, it will be different probably. But in our case, if we go for 800 milliamps a square centimeter, the degradation increases a lot. And the third one is the fluctuation, is the ramping down, ramping up, and so on. Not the pressure, not the temperature. Let's say that's more, the temperature is more related with the efficiency probably. And the pressure is not, well, has a lot of problems because you need to have seals that support the pressure and so on and so on. But it's not affecting to the durability, at least from the test that we have been performing.
Any difference?
Yeah, it is definitely different for PEM. I would agree that pressure and temperature are not as much of a concern in that we control those variables. So the approach we've taken with our scope of supply today is that basically anything going to or through or from the stack is under Accelera's control so that we can warranty the product. And that includes managing the pressure and temperatures. We actually run a balance stack. So whether we're running at 2 bar or 30 bar, the membranes don't really see any difference. So pressure and temperature swings have a mechanical impact on the stacks, but because we're managing them in a reasonable, we're not thermal shocking nor are we pressure shocking the equipment. So it doesn't have an impact on durability, immediate impact. So in, say, a solar coupled diurnal cycle, you're going to be starting and stopping every day, but that's understood and part of the application. So startup and shutdown is not a concern, and we don't limit the number of starts and stops with our equipment. Similarly, with the current density, we want to see how the equipment runs over the entire current operating range. And I mentioned earlier that current and production are proportional, directly proportional. So again, we do not limit our equipment in its use throughout the operating range. I would say with PEM, the number one durability impact is water quality. We're very paranoid about the water quality, and we have in like the 1000, for example, we measure it in 4 different locations, and the water going into the stack will actually stop the equipment if it's off spec, because it has a very significant impact on durability and lifetime. The other parts, though, in terms of, as I said, we don't control the starts and the stops nor the current density, but that's part of the flexibility. That's the advantage the product brings. And as we're collecting more data, we're trying to understand, which one has a bigger impact, a bunch of starts and stops and variable load cycles, or a reasonably steady state operation at a higher current density. Both have an impact, but it's still a little unclear as to which one is a preferred operating mode for PEM technology.
Thank you for both contributions. We are coming to the end of this discussion. It's a pity because we could be the whole day here, the whole day. So next time we should focus on just half-day workshop, talking about challenges and innovations, because there are a lot of them. But just to finalize, I would like to make a question. Future. What is the future developments for each of you? Where you see, as far as you can share with us, where would go the electrolyzer, the next generation electrolyzer? Maybe it could be about high pressure, higher than the state of the art, not maybe about the size. I don't know. What is your impression on this?
I can start on this one. So I mentioned earlier a little bit about our stack technology roadmap. As we get into much larger systems, and by that I mean starting to get into like 500 megawatts plus into giga scale, the exact scope of supply for a technology manufacturer is still a little TBD. So we're working right now with our partners, our customers, to understand what is the right boundary. Obviously, everything around the stacks will want to still maintain control over that, but other parts, gas, liquid separators and pumps, maybe not so much. So as we move into the larger scale applications, it really comes down to the stack. And that's why we're looking at increasing the capacity of our stacks to reduce the number of stacks needed per installation for a given output. So that's really where the core of the technology is, the stack, and that's really where the main focus is. But yes, we're absolutely looking at the complete package in order to be able to offer those really critical guarantees and warranties to the market. So that's part of what we're exploring right now.
Thank you, Anne. Yeah. Javier, please.
Yeah, well, in our case, we are focusing on the technical development in order to increase or to improve the efficiency, to reduce the degradation rates and so on. It's true that you mentioned before that we are putting an eye on different technologies that could be a next generation for example, the anionic exchange membranes. We want to take a look on this, on the evolution and so on, because as you mentioned, it's joining the advantage of both technologies, PEM and alkaline. And in our case, apart from the technical aspect, we want to focus therefore on cost reductions. And at the end, the competition is coming, for example, from the east and so on, and we need to reduce capex. So industrializing, economy of scale, making better manufacturing processes for components. But also we want to take a look on the OPEX, let's say. So we want to develop as much as an autonomous operation that we can, and remote operation. At the end, the maintenance cost from 3% to 5% yearly from the capex is killing some projects, let's say. So we want to reduce this also, but in the alkaline. And in the future, let's see what comes.
Thank you very much. Thank you for your contribution today. Thank you for the discussion, and thank you all for your attention.
Thank you for the questions.
Thank you.
Okay, thank you once again to all the all the speakers. We have learned a lot today, and now we have the pleasure to have with us María Molina. She works for Repsol, Petronor, and she will explain to us real-world challenges within real operational facilities. Please join with us, María. And only to say, because we don't have a lot of time, she brings more than 20 years of experience working within Repsol Petronor, and in the last years, she's responsible for the development of the hydrogen projects within the Repsol strategy. As well to say, Repsol is a key partner within the Hydrogen Technology Observatory, and the stage is yours. Thank you very much.
Thank you very much, Igor, for your introduction, and thank you, Enagás, for inviting me to participate in this technological workshop that could bring us the possibility to share our technology knowledge and to boost the hydrogen business development. I'm delighted to present the key learnings from Repsol Petronor first hydrogen facility. But first of all, I would like to explain very shortly the Repsol strategic path in hydrogen that is based on the Repsol commitment to net zero emissions by 2050. And very important thing is that in the period 2024 and 2027, low carbon initiatives will account for more than 35% of total investment. That is a high amount for us and a high effort. And how are we going to transform our sites? Well, our thought is transform our sites in Iberian into renewable platforms. For example, using renewable hydrogen from electrolyzer or biogas is instead of gray hydrogen for the production of low carbon liquid fuels or direct use as fuel gas. Also to produce advanced biofuels or circular plastic based on wastes, and CO2 capture from air and also from existing facilities that mix with the renewable hydrogen to produce synthetic fuels. But of course, our idea or the goal is decarbonize mobility, not only with the renewable electricity, also with low carbon fuels. And very shortly, our ambition is based on leveraging Repsol industrials and partnership capabilities. And we have targets and CapEx that have been to be adapted according to the opportunities driven by regulation and market opportunities. Both of them are very important, and that's why our ambitions have changed since we started. Right now, in 2027, our goal is to reach 0.3 to 0.4 gigawatts equivalent renewable hydrogen, and also into 2030 to reach 0.8 or 1.2 gigawatts equivalent renewable. And to implement such an ambition plan in 2021, Repsol decided to create the hydrogen business unit and launch a pilot electrolyzer project at Petronor's refinery. Petronor refinery is in Muscat. I present you. This is a picture of it. Is the largest industrial consumer of hydrogen in northern Spain, with an annual consumption of 50,000 tons. The refinery's hydrogen production currently generates approximately 400,000 tons of CO2 emissions per year. Here I present you our 2.5 megawatts electrolyzer. That is Repsol first to produce renewable hydrogen on a demonstration scale in an industrial complex. I present you a schematic diagram of the electrolyzer plant. The first of the principal items and description of this plant. The technology is a low temperature alkaline. The technologist is John Cockerill. We built this electrolyzer with Sener. It was the engineering selected to build this electrolyzer. The module of the stack is 2.5 megawatts, and it can produce around 375 tons per year of hydrogen. With an efficiency beginning of life of 52 megawatts hour per ton, and we can obtain a purity after purification with the specs of mobility. The pressure is around 30 bars, and the outlet temperature is lower 50 degrees centigrade. I can say that after the test run, we can show you that these parameters have been reached. Why to choose, and after that interesting discussion between PEM and alkaline, but why to choose alkaline technology? The main reason was the technological development potential when we started with this project in 2021, because both alkaline and PEM technologies, as we have heard, have similarities in efficiency and in that phase operating an operating rate. But alkaline technology in that moment had more production benchmarks and lower capital costs. But also we were very focused on mitigate risks associated with the supply of critical metals. And also the supply chain security was another very important issue in that moment. I remember we were passing the COVID and all the problem that we had there, based on the European manufacture. The objectives of the project were several, but the main ones was to integrate at an appropriate initial scale different uses of hydrogen, because we can use this hydrogen for the refinery, also for the mobility logistic, because there is a pipeline that connects to a HRS. Also for residential sector in the Avanto Technology Park, hydrogen distribution by pipeline. The idea is to test all these several uses. Also, another very important objective is to generate internal knowledge and experience within Repsol in the engineering, commissioning, process integration, and operation of hydrogen assets. And of course, it's a very important issue for us, the integration into the industrial hydrogen network that we have in our facilities. And also another objective was to develop a digital molecular traceability tool, because it's very important to show to certify the renewable origin of the hydrogen, as well as a tool to optimize the use of renewable sources. Okay, the journey began in March 2021 with the approval of the conceptual engineering. You can see here all the milestones of the project. The investment approval in September of 2021, and also the positive resolution of the environmental permits. And well, it took nearly 2 years to obtain the first hydrogen molecule. And it was a very hard, very hard journey, but with a lot of learnings. And that's the main. What learnings? Or here I can, well, the main ones. I think we continue learning. It's not something that have finished today, but related to the lesson learned during execution and commissionings, I want to highlight that it is crucial, the effective coordination among various disciplines. Also, is essential for the successful execution of simultaneous work, the clearly definition of the critical stages of the projects. For us, the specific installation procedures and thorough cleaning of the circuits were required with new services that we haven't previously in our refinery, as for example, the oxygen. This was another learn. Of course, the need to find the balance between the compact design that we have very compact, but against the practical operability and maintainability, something that has been a very good learn. Also, programming and synchronization between PLC and the transfer rectifier is key to ensure the proper communication and startup sequences. It were hard for us to start up. During the startup, we found difficulties during the stabilization of internal component of the stack, because the small particles from the component of the stack clogged the filters. Therefore, robust filtration system and critical cleaning protocols are required. The next step is, of course, the industrial scaling. Repsol is ready to develop the next renewable hydrogen projects at all Repsol's industrial facilities in Iberia. For us, the next ones are the 10 megawatts electrolyser in the port of in the north Spain, also in the port of Bilbao, that is linked to the first demo synthetic fuels plant that we hope to be running in the end of 2025. And also a small electrolyser, 4 megawatts in the Sines site, in the Sines hub, that is going to produce the hydrogen needed for our, I think, one of our major investment in the petrochemical sector in Iberia. But for us, that knowledge is going to help us to develop our biggest electrolyzer in this first stage in our pipeline of the project, that are the 100 megawatts in Petronor refinery also, and 100 megawatts in Cartagena refinery. Both of them has obtained the IPCEI grant. Next week we obtain it with the and also the Tarragona 150 megawatts that is going to produce the hydrogen, renewable hydrogen, to feed also Ecoplanta, that is one of our also transformation project of our complex. Therefore, in summary, Repsol Petronor 2.5 megawatts electrolyzer has provided valuable insight into technology, operational parameters, and continuous improvement. These learnings are instrumental for the future of renewable hydrogen in Repsol. Thank you very much for your attention. I hope this presentation has been informative and useful for you.
Hello, thank you very much, Maria, for your presentation. And thank you all the panelists and speakers today, the Aragon Hydrogen Foundation, Accelera by Cummins, Nordex, and Repsol for their exceptional contribution today. The technological development of electrolysers, the focus of this workshop, is crucial for advancing green hydrogen as a key energy vector. To conclude, let me highlight some of the, it's not an easy job because a lot of information has been shared, but let me highlight some takeaways. First of all, I would say both companies, Nordex and Cummins, Accelera by Cummins, sorry, are located, or they have their manufacturing plants located here in Spain, Europe. This is an important, in our opinion, is an important fact to say, okay? We say the second one, these two technologies are at the commercial stage, okay, and they have complementarities. I can guess that they are competitors as well, but as far as we know, there are new installations or new projects developed with the two technologies in the same project. So it's true that the complementarity is there, okay? Real facilities. We have been listening, thanks to Murray, Javier Fernández, that new facilities are happening, and the power installed is multiplied by 2 or 3 every year. And these are good news. Scalability. You are scaling up your technology, an important issue to tackle, and every year doubling your power. Very good news. And I would say the last one, and maybe the most important one, is the efficiency improvements. I have done my calculations, and Nordex has said that they are improving, or their target is to improve the efficiency in 10% in the next coming years. This is an important issue to tackle, and we encourage you, Cummins and Nordex, to work hard on that, okay? Because we would say that this increase in efficiency will help to decrease the level cost of hydrogen directly. And it's important to reduce the CapEx requirements and as well to reduce the needs of renewable electricity, okay? And finally, I would say, and we encourage Repsol Petronor to continue developing projects as the one you have done in developing Bilbao, Petronor. We encourage you to continue developing this kind of projects, okay? We don't have a lot of time. We are out of time. So I would say thank you very much to all the online and presential attendees. We will continue within the Hydrogen Technology Observatory developing new workshops in relation to another topics. And thank you very much and have a wonderful day.